Human Anatomy and Physiology. Here we are in episode 5 of our respiratory lectures, and in particular, we will speak about gas transport. So to get started, here we have respiratory volumes and capacities shown on the graph. So these are standard definitions that speak to the different volumes and capacities that exist within the respiratory system. So you can see here that these are just general guidelines, averages, but that the respiratory system in terms of the total lung capacity can include up to 6 liters or 6,000 milliliters of air. And in particular, this can be divided a number of different ways. And so we have the residual volume, which is the volume of air that always resides in the lungs. So there is always a small amount of air always inside of the lungs, even after a maximal exhalation. And the residual volume makes breathing easier by preventing the alveoli from collapsing, and it's dependent on a number of different factors, but it can be a very important indicator of health. Next, we have the expiratory reserve volume, and that is the volume of air that exists and that you can forcefully exhale past a normal tidal expiration. And so that's over a liter of volume for males. We also have the inspiratory reserve volume, and that's produced by a deep inhalation past a typical or tidal inspiration. And this is the extra volume that can be brought into the lungs during a forced inspiration. Lastly, we have tidal volume, and that's simply the amount of air that normally enters the lungs during quiet breathing, and that's only about 500 milliliters or about half a liter of air. So all of those volumes combined speak to the different respiratory volumes. The combination of those volumes, as you can see on the right-hand side of the screen, speak to the respiratory capacity. Next, if we look at two key terms, ventilation versus perfusion. And so these are two important aspects of gas exchange in the lungs. Ventilation refers to the movement of air into and out of the lungs, and perfusion is the flow of blood in the pulmonary capillaries. For gas exchange to be efficient, the volumes involved in ventilation and perfusion should be compatible. Essentially, they should match. However, there are other factors such as regional gravity, gravity effects on the blood, blocked alveolar ducts, or disease that can cause a mismatch in the ventilation and perfusion ratio. So when we look at this ratio, the V to Q ratio, that stands for the ventilation to perfusion ratio. Once again, that's the ratio of airflow to the alveoli in comparison to the blood flow to the alveoli. And we want efficiency of gas exchange to be maintained when we have V and Q closely matched. This really ensures that CO2 is removed from the blood, and that at the same time that the blood is fully saturated with oxygen. There are cases where we have low O2 and high CO2, and that will cause constriction of the arterioles and bronchial dilation. At the same time, we have instances of higher than normal oxygen and lower than normal CO2, in which case the arterioles will dilate and the bronchioles will constrict. This next slide speaks to the partial pressure and the total pressures of gases. So the major gases include oxygen, and we also have a partial pressure of nitrogen as well. And what we're speaking to here is the partial pressure, and that's essentially the force exerted by a gas. And so the sum of the partial pressures of all the gases should equal the total pressure. And so when we're speaking about air, we're speaking primarily about oxygen and nitrogen. Once again, atmospheric air does contain primarily oxygen, but also there are smaller components of nitrogen, water, carbon dioxide, and other minor gases. The relative concentrations of a gas does not change even as the pressure and volume of the total gases change. And lastly, gases will flow from areas of high to low pressure, so the partial pressures of inhaled and alveolar air determine why oxygen goes into the alveoli and why carbon dioxide leaves the alveoli. On the next slide here, what you can see is this ventilation and perfusion matching with blood passing by the alveoli, allowing for carbon dioxide to leave and oxygen to make its way from the alveoli into the blood for adequate perfusion. And this brings us to the concept of Henry's law. So Henry's law speaks to the partial pressures of the gases, and gases once again diffuse from higher concentrations to lower concentrations. Henry's law predicts how gases will dissolve in the alveoli and bloodstream during gas exchange. In particular, the amount of oxygen that dissolves into the bloodstream will be directly proportional to the partial pressure of oxygen in the alveolar air. Notably, gases will diffuse into a liquid based on their partial pressure and solubility into the liquid. Gas solubility will affect the rate of diffusion. And notably, carbon dioxide is 20 times more soluble than oxygen in plasma and alveolar fluid, significantly more than that of oxygen, which is only sparingly soluble in plasma and alveolar fluid. Notably, these gas molecules will diffuse into a liquid from its environment and dissolve in the liquid until the partial pressure of the gas in the solution becomes equal to its partial pressure in the environment of the liquid. For example, what I mean by that is that the arterial blood oxygen and CO2 partial pressures should be equal to that of the partial pressures of oxygen and CO2 in the alveoli themselves. And so that in itself is Henry's law. Next, we have Dalton's law. With Dalton's law, it essentially states that at any given time, the percentage of each of these gases in the air we breathe makes its contribution to the total atmospheric pressure, and this contribution will depend on how much of each gas is in the air we breathe. Dalton's law also implies that the relative concentration of the gases, and what I mean by that is their partial pressure, does not change as the pressure and the volume of the gas mixture changes, such that air inhaled into the lungs will have the same relative concentration of gases as the atmospheric air. In the lungs, the relative concentration of the gases will determine the rate at which each gas will diffuse across the alveolar membranes. If we combine this with Boyle's law, which is all about pressure and volume, once again, the partial pressure of a gas in a liquid will be determined by the amount of that gas that is dissolved in the liquid which in turn is determined by the partial pressure of the gas in the environment of the liquid. And it's all based on those pressure and volume relationships. When there is a mixture of gases, any one gas will move in response to its own pressure gradient. On the screen here, you can see the partial pressures in the air and the tissues at a steady state and at a normal atmospheric pressure. Once again, in the atmosphere, we have oxygen and nitrogen. As we start to move our way towards the alveolar gas, the arterial blood, and the venous blood, and the cells, we see the proportions change. And lastly, this brings us to airflow in the airways. Air velocity, or the speed of flow, is high in the upper respiratory tract, where the total cross-sectional area is actually very low. Airflow will slow considerably in the alveolar airways because of the high total cross-sectional area of all of the alveoli. This is similar to what's happening in the blood vessels.